discussing the packing efficiency. And in the packing efficiency, we have completed with the packing efficiency of simple cubic unit cell with 52%. This concept we have derived with the help of the diagram, in which we have discovered that whenever we are taking our simple cubic unit cell, in that particular case, only 52% space is occupied, other is left with voids like as octahedral and tetrahedral voids. That means 52% is the space which is actually shared, which is actually completed by the atoms or the molecules, which is the solid. Whereas the other left space is there, just the hollow space. Okay, so this was all about the packing efficiency. Now, you know very well, as we have discussed in our last 2-3 lectures, we have total 3 types of unit cell. The first one is simple unit cell, which shares only the number of atoms only and only at the corner. And we have also calculated the actual number of atoms present over there, which is equals to 1. Then we have body-centered unit cell, in which we have the number of atoms present on the corner as well as a particular atom which is present in the center of the body. And what we have calculated, that the total number of atoms there must be equals to 2. 1 plus 1 equals to 2. And the lastly, we have the face-centered unit cell, in which the number of atoms are present at the corner as well as the center of each face. And how many faces we have? We have total 6 faces. Okay, so there are total 3 plus 1 equals to 4 number of atoms. Okay, now in the simple cubic unit cell, we have calculated the packing efficiency. Now we're going to move with our second concept, that is the packing efficiency in face-centered unit cell. Okay, so let's see what actually the face-centered unit cell wants have the total packing efficiency. Okay, the face-centered unit cell, or also we can say it hexagonal close packing or the cubic close packing, that is the same way. Now start. As you know very well that we have total number of atoms present at the corners as well as at the face of the center. And you know very well, we have been discussed, as we have discussed in the previous simple cubic unit cell, that each dot represents a constituent. It could be atom, it could be molecule, or the ion. And the atom in chemistry is represented by a solid sphere. An atom in chemistry is represented by a solid sphere. So there is a solid sphere which represents atom on the corner. Same as it is, there is a solid sphere which represents atom on the corner. Sorry for that. And this particular sphere represents actually the atom which is present over the center of the face. This is known as the face-centered unit cell. Okay, so we have total 3 number of spheres over here on the face. All the other spheres are not shown just for the sake of simplicity. Okay, so now let's start. We know very well that in our cubic unit cell we have different type of edge length which are equals to A, B, and C. So let's assume that this is our AB, this is BC, and this AB represents our edge length, which is equals to A. I'm sorry for this. This AB represents a unit cell edge length with A. Same as it is, this B to C is also representing A. Now, we are assuming that this A to C is actually representing a diagonal which is equals to B. Now, if you see it very carefully, let me show it here. This seems to be a triangle. This is a triangle A, B, C. And now let's move to our lower classes in mathematics. What we have in mathematics, we have Pythagoras theorem, which represents that in Pythagoras theorem, if we have a perpendicular way, if we have base and if we have hypotenuse, then it represents, according to Pythagoras theorem, that AC square, that means the diagonal ka square, that should be equals to AB square plus BC square. That is the sum of the perpendicular, the sum of square of perpendicular plus the square of the base. Okay, so on the basis of this, we will calculate our packing efficiency. How we will calculate? Let's see. So this triangle ABC, where A to C represents B square and AB and BC are just representing A square. That means B square equals to 2A square. Okay. Now, we know very well that in the last class, when we were discussing about the simple cubic unit cell, what we have done, we have calculated on the basis of these spheres, the radius of the sphere. And we have assumed that the radius of a sphere is equals to R. Okay. So how many R would be here? This sphere is half over here. This is just half of, this is complete square, then this is just half of sphere over here, same as it is half of sphere over here, and a complete sphere over here. Okay, so that means if this is representing R, the radius is representing R, then it would be representing 2R. Okay, so how many radius would be equals to R plus R plus R plus R? That means there is 4R. Now, on the basis of 4R, this B represents our total 4R because we have 3 spheres over this B, like this. Okay, so can we represent B equals to 4R? Yes, we can represent. Now, we have to calculate the relation between the radius and the edge length, that is between R and A. Just we have done in the simple cubic unit cell. Okay, so what will we do? We will just relate these two formulas with each other. That is, if I'm just going to under root the square, it would be equal to under root 2a. If we have to calculate b, would it be under root 2a? Yes. So b equals to 4r equals to under root 2a. And if we have to calculate r, then it would be root 24 divided by 4a. And if I would further solve it, how would it be? 2 multiply 2 into a, and after simplifying, the formula would be equals to 2 under root 2r. Sorry, this is a representing 2 under root 2r, and if I'm representing r, it would be a divided by 2 root 2. Okay, so now we have calculated our radius, which is equals to a by 2 under root 2. So we will proceed the same procedure as we have done in the last class. What we need to do, we have to calculate first the volume of one sphere, and then we have to calculate the volume of the whole cube. Let's do this. Now, what actually the volume represents, you know very well that in our face-centered unit cell, there is total 4 number of atoms present over here. Okay, so if we have to calculate the volume of one sphere, what is the formula of volume of sphere? In the lower classes we have done, this is equals to 4 by 3 pi r cube. And what is our r? R equals to a by 2 under root 2. And we have to calculate the volume for the 4 spheres because we have actually 4 number of atoms present in the face-centered unit cell. So it would be equals to as 4 atoms. Okay, ji. So it would be 4 multiply 4 by 3 pi a by 2 under root 2 cube. Okay, this is the first thing. Now, same as it is, we have to calculate our cube, and the cube represents the formula is of cube, volume of cube is side multiply side multiply side, that is a cube. And after putting the whole we would get a cube, that is volume of cube, equals to 2 under root 2 r cube. Yes, we can say a equals to 2 under root 2 r. Okay, now what is the formula of packing efficiency? We have just done in our simple cubic unit cell. That would be volume of the lower one, that is volume of the sphere divided by the volume of cube, multiply 100. And after solving, after putting the whole equation, what would we get? We would get 72.4 percentage. What would we get? We would get 72.4 percentage. Okay. So this was all about the packing efficiency of face-centered unit cell. Quite simple. We have just taken the 3 spheres because the face also has 3 spheres. Okay. On the basis of this, we have calculated volume of 1 sphere, and we have total 4 number of FCC. Oh, sorry, 4 number of atoms in FCC. So it would be 4 multiplied 4 by 3. Volume of cube equals to a cube. We will calculate, and after solving the whole equation, what would we get? The packing efficiency would be 72.4%. So it would be the result for FCC. Okay. So now we are left with only one, that is body-centered unit cell. And I leave it to you. You have to calculate the body-centered unit cell by yourself, by your own. Just try with your notebook, and I'll try to explain it with little bit, but I'll not solve the complete formula because it has the same method. Okay, so let's start and complete this topic, the packing efficiency, and then see what would the next topic. Okay, now we have done with the simple cubic, we have done with the face centered. Now let's do with the body centered. 52%, 72%, and now let's see who will the winner, who will get the maximum packing efficiency. Now, what's the new beginning? What's the new deal in the body centered unit cell? That is, there are number of atoms present over the corner, and the new thing here it is, there is one atom present in the center of the body of the complete unit cell. So there is a kind of sphere present over here. One is over here, one is over here. So you will get the idea how can we calculate. Okay. I'm sorry. Just as we have done in our face center, we have put out these 3, and we will try to calculate with the help of diagonal. We will do the same procedure. We will put these 3 in the same diagonal, and we will try to calculate with the help of Pythagoras theorem. Just the same concept, same formula. Try yourself on. I'll just writing the exact answer. Okay. I'm just writing the radius first of all. The radius over here is equals to under root 3 by 4a. Okay. And the packing efficiency would be, what is the formula of packing efficiency? Or we can say volume of atoms divided by volume of unit cell multiplied by 100. Please type your own. It has the same formula. This would seem little bit now that we have complete diagonal. We will put the same Pythagoras theorem as we have done in face center, exactly the same procedure. Okay, but the concept would be little bit changed due to the number of size of spheres, and the Pythagoras theorem would be changed. Okay, so we have radius here equals to under root 3 by 4a. And how many body centered unit cell has the atom? Actually, it has 2 atoms. So it would be 2 into 4 by 3 pi under root 3 by 4 a cube, and a equals to 4r by root 3 cube multiply 100, and we will solve the whole concept. And what would we get? We would get the exact formula and the exact answer, which is equals to 68%. So on the basis of these 3 unit cells, these 3 calculation, what we have came to know? We have came to know that the face centered unit cell has the maximum packing efficiency, which is equals to almost 72.4%, almost 72%. Okay, so with these three concepts, we can easily derive that yes, the packing efficiency in the face centered unit cell has the maximum on its own. Okay, and if I'm trying to put the old radius also in simple cubic unit cell, the radius is equals to, is there doubt? Simple cubic, face centered, body centered. R equals to a by 2. What was in this in face centered? A by 2 root 2 root 3 by 4a. Okay, this was the radius, this is the packing efficiency. All right, class, this was the whole topic about packing efficiency, in which we have calculated how actually the solid is packed whenever we put a unit cell over and over again and again to make a complete crystal lattice, and we have got that FCC has the maximum packing efficiency. All right, so this was the topic by packing efficiency. Now we will just finish with a short topic, and then we will have your doubts and queries. Okay, so now let's move with the last topic of today's class. We have to calculate the calculation of unit cell dimensions. I'm going to rub this. Now we have just a simple formula that if we have to calculate the density, it would be equal to this. Let me represent what these actually represents. The density is equals to Z into M divided by NA A cube. Now what Z, M, and A, these all terms defines to us? Okay, let me tell you one thing. You know very well, the density is equals to mass per unit volume. That means mass is covered and divided by volume of a unit cell. Okay, so now in this concept, we are having the Z, the M, the Avogadro number, and the A. What these all terms represent to us? Z represents the number of atoms in a unit cell. M represents the mass, and A represents the Avogadro number. What is the Avogadro number? This is equals to 6.022 into 10 raised to power 23. I'm sorry. And the last one, A represents edge length. We will just see a simple numerical formula, and then we will finish the class by taking your quiz. Okay. So now, first point is how we will remember this. This seems to be very easy, that we have just 4 concept here, just 4 constant here, Z, M, Avogadro number, and the edge length. But whenever we go to your exam, and this all Z, M would seem to be moving and rotating, and we would be a little bit confused. Okay, so I have just remembered this by a simple concept: jump na, jump na, ZM, jump, Na, Jamna. Okay, this is my concept that I have remembered to calculate the density. There is a simple formula, Jamna, where Z represents number of atoms in unit cell, M represents the mass, and A represents the Avogadro number, and A represents the H. Okay, let's have a simple numerical formula over it. Okay, we have example 1.3. The silver forms cubic closed packing, and X-ray studies of its crystals show that the edge length of the unit cell is 400.6 picometer. So let's write. Atomic mass is also given. Atomic mass is 107 unit. So we are given with cubic closed packing lattice, CCP. And I have told you the hexagonal closed packing, the cubic closed packing, and the face-centered unit cell. These all three terms are equal. These all three terms mean the same. Okay. So cubic closed packing, that means we are putting the face-centered unit cell. So Z must be equals to 4. And the atomic mass is given 107 unit. The edge length, that means A, which is given to us 400 picometer. You know very well what is picometer. How can we calculate it into meter? It would be 408 into 10 raised to power minus 12 meter. Okay, so we will put all this concept into it. Density equals to 4 into 107. What is Avogadro number? 6.022 into 10 raised to power 23. Multiply A is 408 into 10 raised to power minus 12 cube. We will solve it and we will get our density. Okay, and the beauty of this formula is not only density. On the basis of this formula, we can also calculate our mass. We can calculate our Z over here. We can calculate edge length over here, because there would be density given. So out of these 5 constants, the 4 would be given to you, and you would easily calculate the 5th one. Okay, this is the beauty. This is the simplification of this formula. This is the advantage of this formula, with the help of which you can easily calculate your constant. Okay, so this was all about this topic. Now we are left with only imperfection and the magnetic properties of the solid state. Okay, so let me just recapitulate and then we will have your doubts. Okay, let's start. We have just done the packing efficiency, in which we have calculated the simple cubic unit cell packing efficiency, the body centered and the face centered, and we have come to know that the face centered has the maximum packing efficiency 72%, and the same as it is, we have put just a simple numerical formula, that is density equals to Jamna Z into M divided by Na into A, where A is edge length, Z is the number of atoms in unit cell, and M is the mass. Don't mess up that what is given cubic closed packing or hexagonal closed packing. This all equal to face centered unit cell. Okay, so we can now easily calculate and easily complete this question. And I told you about the marking scheme, that in the solid state we have completed our 3 to 4 marks till yet, and this was the last topic in which we can easily cover our marks. Okay, this numerical formula can come either this one or the numerical formula with the molecular formula. Okay, only out of these formula, these 2 numericals, you will get 1 numerical in your board exam. All right, bache? So this was all about it. Now we are left with only magnetic properties and imperfection that we will do in our next week, and we will finish our 2 chapters in the chemistry. Now I want to ask your queries and doubts, what you have and what I have delivered to you. Let me know. So please let me know your doubts and queries. Sir, how